So here we have question 7. Again, it's worth 50 marks, as are all the questions in the paper, and my email is there again on the screen if you have any questions or comments about the marking scheme. Okay. So we start off with our definitions. As always, definitions asked in equilibrium, but quite often, so make sure you know those well. So what is meant by chemical equilibrium? Why is it described as a dynamic state? And Staelowitz principle. So chemical equilibrium is a state in which the rate of forward reaction is equal to the rate of reverse reaction, or you could say the state reached at which concentrations of reactants and products are constants. And again, remembering that the bold print is the key phrases that you need. So 5 marks there for either one of those two. Why is it described as dynamic? Because the reactions continue, or the reactions don't stop, or the reaction doesn't stop, so 3 marks there. And then on to Le Chatelier's principle, systems at equilibrium react to oppose applied stresses. So you mentioned equilibrium for 3 marks, and then oppose stresses, say that in some form outlined in the answer there for another 3 marks. And you can see the options given underneath it at the end there. Okay. Sulfur trioxide decomposes to form sulfur dioxide and oxygen at a temperature T1, according to the equilibrium shown. And the graph shows the concentrations of sulfur trioxide and of oxygen over a period of 6 minutes at temperature T1. So things to note here, delta H is positive, so it's endothermic in the forward direction. SO3 starts at 0.4 and reduces down to 0.1. O2 starts at 0 and increases up to 0.15. So state the time to the nearest minute when equilibrium is first established and explain your answer. So the time is 3 minutes, because this is where the concentrations of O2 and SO3 remain constant, or you could also say that the curve flattens out at this point. So 3 marks there by 2, giving you 6 marks. So copy the above graph onto graph paper and sketch on the graph how the concentrations of sulfur dioxide changes over these 6 minutes at temperature T1. So in order to do this, we need to do a little bit of calculating first, okay? So we see there that the SO3 starts at 0.4, so we put this in our graph. The oxygen starts at 0, we can see that from our graph down here, and obviously the SO2 will start at 0 too, because it's a product, I should say, okay? We see then that the SO3 reduces down to 0.1, okay? So here we have our 0.1, so our change is minus 0.3. Okay, so we apply our ratio, which is 2 is to 1 to the change line. So it's 0.3, 0.3, and 0.15. And we're subtracting from the products, from the reactants, sorry, and we're adding to the products. So that gives us, we know oxygen is 0.15 already, and it tells us that SO2 then, which is what we're looking for, is 0.3. So we draw our line then starting at 0 because it's a product, going up to 0.3 in the concentration and 3 minutes in our time, similar to the other two curves. Okay, so showing that the curve flattens out at 3 minutes for 3 marks and rises to a height of 0.3 on the y-axis for another 3 marks. Write the equilibrium constant Kc for the above reaction. So again, 6 marks there. That's 6 marks you should be getting every time without fail. All right. And then calculate Kc at temperature T1, and you should have some of this work done already, which you would have had to do for the graph. And you can see if your equilibrium line, which we talked about it in the previous part, 0.1, 0.3, and 0.15, you just fill that into your equation, and you get 1.35. So 9 marks there, 3 marks for doing what we had already done, and then your calculation at the end, just filling that in there and getting the answer of 1.35. So that's a nice enough equation, not overly difficult. I suppose the preceding part was a bit trickier, all right. Okay. Then on to the last part, which was about the temperature. So the temperature of mixture was changed to T2, and the mixture was left to establish a new equilibrium. In the equilibrium mixture, the concentration of sulfur trioxide was found to be 0.07 moles per liter. So, and we saw previously that the equilibrium concentration of SO3 was 0.1, okay? So that has reduced the equilibrium concentration of SO3. Deduce which of T1 and T2 is the higher temperature and explain your deduction. Okay, well, the equilibrium concentration of SO3 is lower, so that means the equilibrium has shifted more to the right-hand side, okay, because there's less SO3, which means there'll be more products, okay? So it has shifted in the endothermic direction. So what causes a shift in the endothermic direction? An increase in temperature or a higher temperature favors the endothermic direction. So this shows that T2 is the higher temperature. Okay, so I hope that's clear. Any questions about that marking scheme for that question? Okay, please email me and I will get back to you as soon as possible. Okay, that's it. That's question 7 done and dusted.